So let's step a little bit further out. That's a successful, we think, theory for the origin of the moon. Let's move out now in the solar system to the sun. Here's a beautiful picture of the sun. The sun, it's worth reminding ourselves, can fit 1 million Earths inside. So you could fit 1 million planet Earths in that ball of gas. It shines by burning 600 million tons of hydrogen gas every second and converting it into helium, a process called nuclear fusion. So it's an incredibly violent and impressive place. But one interesting thing is that in that process, as it shines and produces energy from its core, many of its outer layers get thrown off into space. Actually, 1 million particles per second fly off the sun, and that's called the solar wind. Another way of looking at that is it's 7 billion tons of sun every hour get lost into space. That's an incredibly violent wind of particles flying our way. Many of those, some of those, hit the Earth. And what we know is that if the Earth wasn't protected from that solar wind, then its atmosphere would most likely have been blown off into space long ago, and we wouldn't exist. So what is the explanation for why the solar wind doesn't affect the Earth in that way? Why have we still got an atmosphere? Well, we have to go deep into the heart of the Earth to understand that. This is a slice through the Earth. At its core, the Earth is very strange, actually, because it's hotter than the surface of the sun. So it's hotter than 6,000 degrees Celsius at the centre. But it's solid, which is odd, because you would think if you heated iron, which is what's sat at the centre of the Earth, up to 6,000 degrees, then it would melt, right? Actually, it's under incredibly high pressure, and that keeps it liquid. That makes it solid, even though it's at an incredibly high temperature, and you might think it'd be a liquid or even a gas. So it has a solid iron core. Outside that, there's this thing called the outer core, which is liquid iron, a molten iron core. And that's the key to understanding how we hold on to our atmosphere. Now, I'm going to show you an equation, which is actually written in quite a scary form, because it's the most modern form, the most elegant form you can write it in. But I want to show it you because I think one of the key things for me about physics is that maths is important, but I know that many of you maybe might think that you don't like maths very much. In fact, I could say put your hand up if you don't like maths very much, but no one will put their hand up because you're all superb students. I didn't like maths at school. I mean, I actually got a D at A-level maths, right, which means that I wasn't very good at it. I subsequently found out at university that I enjoyed it, and when I enjoyed it and started practicing, I actually got a bit better at it, or good enough to do physics anyway. I think that's one of the lessons that I learned, that it's like playing piano in a way, doing maths. You can't sit down at a piano and say, I can't do that. You know that you've got to do a bit of practice. I found that. And the maths, though, once you get that in your head, that it is a bit tricky, but you can get there eventually, really helps you understand the phenomena that we're talking about. So this is a bit of maths, and I know it looks a bit weird, right, and it's not the most friendly thing, but it's a very interesting bit of maths. It's one of Maxwell's equations called Amperes Law. So you learn at GCSE that if you have a current circulating around, just a moving electric current, you get a magnetic field, right? That's what we think, or we know, is happening inside the Earth. Because there's molten iron, you can get electric currents flowing, and that generates the magnetic field of the Earth. But this is actually the most advanced and precise equation you can write down that says that. This is a magnetic field, and it tells you exactly how that magnetic field looks when you circulate a current, which is this bit. So that just says electric current equals magnetic fields. That bit actually says also changing electric fields make magnetic fields, and I'm going to mention that a little bit later on. But basically, that says a current makes a magnetic field. That's what we think is happening inside the Earth. You get currents flowing, and that generates this force field, a magnetic field. There's one interesting thing, though, and I wrote it down because it's so interesting, I didn't want to get it wrong. So we understand roughly where the Earth's magnetic field comes from, we don't really understand it properly. For example, it has flipped. So north and south, so we have a north pole and a south pole, and a compass points to the north. It's flipped 170 times in the last 70 million years. right? So the north pole of the Earth became the south pole, and then the north again, and then south again. And it's done it 170 times. We know that by looking at rocks and the way that the little bar magnets inside rocks line up. And because when they're formed, the little magnets point towards where the Earth's magnetic pole is, then you can work out where the pole was by just looking at the rocks. And we found that it keeps flipping. Why that is, we don't know. It's due for a flip now, actually. So one day, in the next few, maybe 100 years, maybe 1,000 years, you'll get a compass out and it won't point north anymore, it'll point south. And we don't understand that. But roughly speaking, we know that because electric currents flow around there, you get a magnetic field. What does that do to the solar wind? Well, it does things like this. This is a beautiful picture taken about a couple of weeks ago from the space station. So this was an astronaut on the space station looking down at the Earth and taking a picture of the south pole of the Earth. And this is the aurora australis, the southern lights. So this is the southern pole of the Earth. What happens to the solar wind is that when it hits the Earth, it hits the magnetic field. And because the solar wind is made of electrically charged particles, it's deflected around the Earth. But that's not all that happens, because the Earth absorbs energy from the solar wind in those collisions, and the magnetic field gets stretched out behind the Earth. So literally, on the dark side of the Earth, pointing away from the sun, you get like an elastic band of magnetic field. And you can't carry on stretching that forever, and so at some point it snaps back and accelerates those charged particles to the poles of the Earth, down the magnetic field lines. And you get a beautiful glowing light, because those atoms of oxygen and nitrogen in the Earth's atmosphere are literally shaken. Light is shaken out of them. That's one way of thinking about it, by this snapping back of the Earth's magnetic field. And you get beautiful displays like this. Here's another one, which I think is absolutely wonderful. It's a movie taken from space, again, over the south pole of the Earth. And you can see that circuit of aurora, the glowing atoms of the Earth's atmosphere, excited by all that power initially from the sun, driven into the magnetic field, and then snapping back again. That's a visible illustration of our protection. And I think it's all the more beautiful when you remember that without that, our atmosphere would most likely have been blown off into space and we wouldn't exist. And it's not only the Earth. This is a picture, 3 pictures of the planet Saturn, taken from the Hubble Space Telescope over 6 nights, 24th of Jan, 26th of Jan, 28th of Jan, in 2004. And you can see the aurora over the south pole of Saturn changing as you go from night to night. And that, again, is due to the fact that Saturn has a magnetic field generated, we think, just like the Earth. So the magnetic fields of planets protect them. They produce beautiful light shows like that, but we don't fully understand them yet. It's still an area of active research. While I'm talking about Saturn, just before I move on, I just thought I'd show you a couple of what I think are the most beautiful pictures taken in the last few years by our army of space probes that have gone out into the outer solar system. This is a picture of Saturn taken by the Cassini spacecraft, which is in orbit around Saturn now. The sun is behind Saturn. You can see the rings illuminated by the sunlight. But the most beautiful thing in this picture is that little spot of light just there, which I can enlarge. So that little spot of light that looks like one of Saturn's moons is in fact our planet, Earth, taken from 1 billion kilometers away. Cassini captured it in this image, hanging between the rings of Saturn, looking back towards the sun and back towards our home planet. So a beautiful picture of Earth seen from 1 billion kilometers away. And whilst I'm on pictures of Saturn, I just wanted to show you these 2 things. Virtually nothing to do with this talk, but beautiful nonetheless. This is another picture taken from Cassini a couple of months ago now. That's Saturn, which is actually in the background of this picture. And that's the moon Enceladus. Now, if you watched Wonders of the Solar System, you would have seen this amazing moon Enceladus, which is about as big as Britain, but has fountains of ice rising up from its surface. We discovered that there is probably liquid water on this tiny moon powering these fountains of ice out into space. That's Enceladus, and you can just see at the bottom these misty plumes rising up from the surface. These are the ice fountains of Enceladus, taken in this beautiful picture. And then Cassini flew very close. This is after we made the TV series. Flew very close below the limb of Enceladus and flew through those fountains of ice. And there it is. So that's the limb of this tiny moon, 1 billion kilometers away from the Earth. Absolutely stunning picture.